Now what's interesting about these types of phase changes and chemical reactions is that they occur without a change in temperature. That sounds a little weird. Well, we're going to think about this. I'm going to take a glass of water, or at least draw a glass of water here. And in this glass of water, I'm going to put a block of ice. And this block of ice is at its melting temperature, 0 degrees Celsius. Actually, let's do this a little different. I'm actually going to do this just a bit different. I don't want to put the water here. That's going to complicate things. We've got to keep this as simple as possible. We're going to take this block of ice and we're going to place it in a sealed container. And we're going to add just enough energy to this thing to start the block of ice to melt. And so what's going to happen while this occurs is the block it's going to start to melt. And when it does so, it's going to form a pool of water. And the way this occurs, as long as you keep everything well stirred and mixed, oddly enough, as this process takes place, H2O solid going to H2O liquid, the temperature stays the same. That's a little goofy. That sounds a little odd. But as the phase change occurs, the temperature of the mixture, as long as it stays well mixed, it doesn't change. So even though I'm adding energy, we could say I've just got a little heater here, just a little heater that's having heat go into the ice to cause it to melt. The ice and the water stay at 0 Celsius all throughout the melting process. Now, how in the world can this happen? I'm supplying energy as heat to the block of ice, and yet it's staying at the same temperature. Well, what's going on here is basically you recognize that the energy that's going into the ice is being used to break apart the molecules. Remember, in a solid, those particles are attracted to one another and they just vibrate. To have the phase change occur, the energy that is used, the energy that's gained, we'll say, by the ice, is not used to increase the temperature, but rather to break the attraction between the solid molecules so that they can start to move freely. So while the molecules still have the same average kinetic energy of motion, they're no longer attracted to one another, and breaking that attraction requires energy, even though the temperature doesn't go up. And so what this means is for a phase change, we can't use this equation. We can't use this equation to find the energy changes that occur during a phase change. Why not? Because there's no change in temperature. During any phase change, delta T is 0. So if we use this equation, we'd find that we're giving energy to a system to get it to undergo a phase change, and yet the energy calculated would be 0. That can't be. So we have to use a different equation to find the energy changes that occur to cause phase changes to happen. And it's really simple. I mean, it's not difficult at all. You just got to recognize you got to use different equations. And in this case, for a phase change, so Q for a phase change is going to be equal to the mass of the stuff undergoing the phase change times the enthalpy of the phase change. That's it. How much stuff are you melting, or whatever, times the enthalpy. Pretty simple. And what we're going to do now is we're going to apply this to the graph that you see on slide 17 of PowerPoint number 5, the energy PowerPoint. And what you see on that particular graph is you see on the y-axis, you see the temperature in units of Kelvin, and then on the x-axis, you see energy in joules. And the way this works is you see a increase in energy. Excuse me, okay, so here's what we're going to imagine. We're going to take 1 gram of water and we're going to cool it all the way to absolute zero. So that's going to be all the way down here at 0 on the y-axis. And we've added no energy to our 1 gram block of ice at 0 Kelvin. Of course it's ice at 0 Kelvin, right? At absolute zero it's going to be ice. And then what we do is we start adding energy to our system. And it's enclosed in a box. We can just add little tiny amounts of energy and watch what happens, measure the temperature. And what we see is as we start to add energy to our ice at 0 Kelvin, the temperature starts to go up. That makes sense. So it starts to rise. And then something goofy happens when we hit 273 Kelvin. What happens at 273 Kelvin is the temperature levels off, even though we continue to give it energy. And then at some point after we've given it a certain amount of energy, the temperature starts to rise again. Up it goes. And that happens to a particular point. And as we continue to give it energy, the same thing happens again. We get a leveling off here. And that happens to happen at 373 Kelvin. And this goes on for a really long time. A really long time. You'll notice there's a really long plateau here. And after quite a long plateau, again, we're going to imagine that this water is entrapped in a container. And then after a particular point, the water trapped in the container, it starts to go up in temperature again. So what's happening here? Well, of course, we start as a solid. And as we continue to warm the solid, the temperature, we add energy, the temperature goes up. And at this point right here, hey, we're at the melting point. You're at the melting point. And so what happens at this point, the very first drop of liquid forms. And as you continue to add energy, the block of ice continues to melt. And at this point, the energy that we're putting in no longer is used to increase the temperature, but rather it's used to melt the block of ice. It's used to separate the molecules so that they can move freely. And that happens here. So here the first drop of liquid forms. So this flat plateau represents the melting process. And here we have both solid and liquid present. And the block of ice continues to melt until this point right here, when the very last piece of solid ice melts. And then once all of the solid has melted, then as you continue to add energy, the temperature starts to go up again. And the liquid gets hotter and hotter and hotter. The molecules start moving faster and faster and faster until here, the stuff starts to boil. Here, the very first molecule of gas escapes. Actually, let me write here. This is the liquid portion. Here, the very first molecule of gas escapes, and more gas molecules form as you move across here. So here you've got boiling occurring. And that takes a lot of energy. It takes a lot of energy to boil water. But once you get here, you've got the very last drop of liquid escaping into the gas phase. So here we have liquid plus gas. And here, the very last bit of liquid evaporates and goes to the gas phase. And if we contain this gas that's formed in our container and continue to heat, then the gas that's produced will increase in temperature. So here we only have a gas.